Hello students, in this video we'll discuss the geometrically invariant definition of the gradient vector. So given a function w of f of x, y, z, consider the level surfaces. F of x, y, z equals k. So if I give you a function of three variables, I can define these level surfaces over here. So there's all these level surfaces like that. That's one. That might be like f equals k1. This might be f equals k2. F equals k2. And these level surfaces foliate three-dimensional space, okay? What I want to do now is define, let's recall, that d in the directional derivative in the direction, let's say, of a vector v of f at a, b, c, this directional derivative, is the limit as h goes to 0 of f of a, b, c plus hv minus f of a, b, c, all divided by h. That's the directional derivative. And in special cases, what we'll do is we'll use the notation. I can use a notation which is helpful for us in later discussions. This is going to be df dv vector at the point a, b, c for directional derivative. There's just different ways of writing the same thing, okay? All right, excellent. So that's the directional derivative. Now what I'm going to do is the following. So we're in a position to define the gradient now. Define gradient of f at the point a, b, c. You can see over there too, a, b, c, to be the directional derivative of f in the direction of the normal vector p hat at a, b, c, and then p hat at the point a, b, c, where p hat is the principal normal vector to the level surface on which the point AB, ABC, f of ABC resides. Great. Now the important thing is this might now look familiar because we're used to saying the gradient is partial f, partial x, partial f, partial y, partial f, partial z. The issue with that definition of our gradients, let's just recall that Calc 3. So normally, you would define something like this, gradient f to be fx, fy, fz, right? And that works in Cartesian coordinates. That works in the standard basis coordinates with directional derivatives. The problem with this is that this is not coordinate invariant. This is not coordinate invariant. You can see it just by rescaling Euclidean space. It doesn't scale appropriately, okay? But this definition is coordinate invariant. This is coordinate invariant. And this coordinate invariant definition is going to help us when we put the gradient in different coordinate systems, like spherical coordinates or polar coordinates or confocal coordinates or elliptic coordinates, or the full Monty of orthogonal curvilinear coordinates, or in terms of just general coordinates with respect to an arbitrary frame, right? So this definition of gradient is going to be very helpful. And it makes sense too what the gradient is. If we recall from Calc 3, we spend a lot of time talking about gradients as the direction of maximal increase. Well, of course, the normal vector is the what? The normal vector to a surface at a given point is the direction of maximal flux, right? So there's a coincidence, that idea, that geometric idea of like the direction of maximal increase is embedded in this definition over here. That's a unit vector. That's the rate. The directional derivative is the rate at which you're fluxing out of the surface. Okay, excellent. Now, what do I want to do with this? Let's sort of analyze this a little bit and get some relationships between a fixed coordinate system, right? And so now what we want to do is this. So let's draw a configuration over here. Let's suppose I have a point P here on a level surface. This is level surface. And I have a point over here, N. And if these are two level surfaces, level surface 1, right? So these are different level surfaces. The function f is constant here, right? So you could say f is equal to k1 over here and f is equal to k2 over there, okay? Great. And I'm going to pick a point Q over here, and then I'm going to draw the arrow from P to Q. I'm going to call that length over there delta S, right? And I'm going to call this length over here delta N. And P to N is in the direction of the normal, right, out of the surface at that point. So that's going to be the normal direction. In other words, Pn is basically in the direction that's normal to the level surface at Fk1. There's an angle between over here, phi. And what sort of can I say about these things if this is normal, right? So if this was normal over here, that's perpendicular like so, then we can say that's what? We can say that the delta S is what? Is going to be, so we have a right triangle over here, right? So if I have delta S cosine of phi is going to be delta N approximately, right, on this scale. And so now if I look at this difference quotient over here using this configuration, what can I say? I can look at delta F, delta S, this directional component, that change is going to be what? It's going to be delta F, delta N, right? And then where does the cosine go? Okay, so if I put delta N, if I put a cosine over here, so I have to put a cosine up here on top, cosine of phi over here on top. So this allows me to get a definition that says the directional derivative of f going from one surface to another. So we can conclude from this that, taking the limit, that df ds, the directional derivative in the direction of p to q, is what? Is df dp for the normal direction. And then what times the cosine of theta? Okay? And so in the limit, what we can do in the limit, cosine of phi is p hat dot t hat, where t hat is the unit tangent vector in the direction from P to Q. Okay, excellent. And so what this allows me to do now is this allows me to write df ds, the directional derivative, in terms of what? The directional derivative from P to Q. So of course, ds is this direction from P to Q, right? So differentially of the ds is going to be dt times that thing. And so now we have what? We have, this is going to be df dp. And then what? Then p hat t. P hat dot t. And so that says this directional derivative is really just what? It's just really just gradient of f dot t hat. And that's a very important relationship, so let's box it, because we're going to use this relationship over and over and over again. The directional derivative of f in the direction s from one level surface to the other can be written as the gradient of f dot the unit tangent vector in that direction, right? So in other words, delta s, that delta s increment and delta t are in the same direction as each other, right? So this increment over here and this increment over here are in the same direction, okay? And then this increment and that increment are in the same direction, so the units balance out, okay? Excellent. And so here's the important thing to remember. So if ds1, if partial f, partial s1, partial f, partial s2, partial f, partial s3 are directional derivatives, in the directions of E1 hat, E2 hat, E3 hat, collection of orthogonal vectors, then what can I say? Then we can use this relationship over here to get the following formula. That what? That the gradient of f is df ds1 in that first direction, E1 hat, plus df ds2, E2 hat, plus df ds3, E3 hat. Now you might say, well, wait a minute, that looks exactly equivalent to the definition that we get in Cartesian coordinates. And indeed, this formula allows us to recover the gradient in Cartesian coordinates if my vectors E1, E2, and E3 are just I, J, and K. Because if E1, E2, and E3 are I, J, and K, this is partial f, partial x, this is partial f, partial y, that's partial f, partial z. However, if we were in different coordinate systems, these bases might be different, because now the coordinate surfaces that you're looking at in orthogonal curvilinear coordinates might have unit vectors which are what? For example, if you think like spherical coordinates, the unit vectors with respect to the basis, the tangent plane basis in spherical coordinates are what? As you move along the sphere, that frame of reference is changing, right? So these E1, E2, and E3 do not have to be constant, right? So that's an important thing to note. Note E1 hat, E2 hat, and E3 hat need not be constant. And since those things aren't constants, we have to look at these derivatives over these directional derivatives relative to the changing coordinate frame as well, right? So in other words, the gradient has to respect that the coordinate frame may be changing, these basis vectors might be changing as you move along. You want to think of this exactly akin to like the Fresnel's array system, right? It's very easy when a curve has fixed tangent vector, unit tangent vector, binormal vector, right? That's a simple situation, but in general, if you have a curve, the principal normal vector, the binormal vector, and the tangent vector are moving along, and they're changing along the curve. The same thing is true for orthogonal curvilinear coordinates and more general coordinate systems. These unit vectors over here, E1, E2, and E3, might be changing as the parameterization of that space of those coordinate frames is changing. So these things have to represent the relative changes. So in further videos, we'll see how to find these gradients in orthogonal curvilinear coordinates by looking at the metric tensor. Thank you very much.